This is the story of three cracks currently running through our picture of the universe. Two independent measurements of cosmic expansion that refuse to agree no matter how carefully anyone remeasures them. Hundreds of galaxies from the dawn of time that look far too developed to exist yet. And a physicist who thinks both of those problems are symptoms of the same underlying issue, a universe that might be twice as old as the number sitting in every textbook. This is a deep dive into the current, unresolved argument over the size, age, and structure of everything that exists, and it starts with the disagreement sitting at the very center of it. Before we get into it, go ahead and hit subscribe, because we're covering the actual edges of what's currently known in cosmology, and there's more of this coming. Let's set up the basic disagreement first, because everything else in this video builds on it. There is a number in cosmology called the Hubble constant, usually written as h0, and it describes exactly how fast the universe is expanding right now, today, at this exact moment. In principle, there should be one correct value for that number, and every method of measuring it should converge on the same answer. In practice, physicists have found two broad families of methods, and they keep giving two different answers, and that gap has refused to close for well over a decade now, despite dramatically improved telescopes, dramatically improved statistics, and enormous amounts of very smart people trying very hard to make it go away. The first family of methods looks at the early universe. Specifically, it uses the cosmic microwave background, the leftover afterglow radiation from roughly 380,000 years after the Big Bang, mapped in extraordinary detail by the European Space Agency's Planck satellite. Using the standard cosmological model to extrapolate forward from those early conditions to today, this method consistently produces a Hubble constant of about 67.4 kilometers per second per megaparsec. The second family of methods looks at the nearby, present-day universe directly. It uses what's called the cosmic distance ladder, a chain of overlapping measurement techniques where each rung calibrates the next, stretching from our own solar system all the way out to distant galaxies. The most influential version of this approach is run by an ongoing research collaboration called SH0ES, short for supernovae and H0 for the equation of state, led in large part by Adam Rees, one of the three physicists who shared the 2011 Nobel Prize for discovering the accelerating expansion of the universe back in 1998. The SH0ES team uses Cepheid variable stars, the exact same standard candles Henrietta Leavitt identified back in 1912, to calibrate the distances to galaxies that have also hosted a specific kind of exploding star called a Type 1a supernova. Because Type 1a supernovae are bright enough to see across enormous distances and explode with remarkably consistent peak brightness, they let astronomers extend Leavitt's original measuring stick out to galaxies far beyond where individual Cepheid stars can be resolved. Running this ladder all the way through, the SH0ES team consistently arrives at a noticeably higher number, around 73 to 74 kilometers per second per megaparsec. Those two numbers, 67.4 and somewhere around 73 or 74, are supposed to be the same number. They aren't. And the size of that gap, measured against the margins of error on both sides, has been reported by different research groups at somewhere between 4 and 6 standard deviations of statistical significance, a level of disagreement that in most areas of physics would be treated as a serious, real discovery of something new, not a rounding error waiting to be explained away. Because a two-method disagreement always raises the obvious question of whether one side just has a hidden mistake in it, physicists have spent the last several years building out entirely new, independent ways to measure the Hubble constant, specifically to act as tiebreakers. This is where the story gets genuinely interesting, because instead of resolving the argument, the new methods have mostly just multiplied it. One of the most important tiebreaker efforts comes from a University of Chicago astronomer named Wendy Friedman, who has spent decades working on precision distance measurements, going back to her own earlier work helping establish the original Hubble constant using the Hubble Space Telescope in the 1990s. Friedman leads a research effort called the Carnegie-Chicago Hubble Program, and instead of relying on Cepheid variable stars the way SH0ES does, her team uses a completely different kind of standard candle called the tip of the red giant branch, usually shortened to TRGB. As stars similar to our Sun age, they eventually swell into red giants, and there's a very specific, very predictable point in that process, right at the peak brightness of the red giant phase, that occurs at almost exactly the same intrinsic luminosity across enormous numbers of stars, in almost any galaxy you look at. That predictability makes the tip of the red giant branch an extremely reliable standard candle, similar in spirit to Cepheids, but built from entirely different physics and entirely different stars, deliberately chosen to avoid any measurement problems that might specifically be affecting Cepheid observations. Friedman's TRGB measurements, published across several papers between 2019 and 2021 under the Carnegie-Chicago Hubble program, have consistently landed right in the middle of the disagreement, around 69.6 to 69.8 kilometers per second per megaparsec. That value sits statistically closer to the Planck CMB result than to the SH0ES Cepheid result, agreeing with Planck at roughly the 1.2 standard deviation level, while still showing some tension, at around 1.7 standard deviations, with SH0ES. In other words, an entirely independent method, built specifically to sidestep any Cepheid-specific measurement issues, still doesn't cleanly resolve the disagreement. It just adds a third data point, sitting uncomfortably between the other two, which is exactly the kind of result that keeps this argument alive rather than settling it. The disagreement between the TRAG team and the SH0ES team isn't purely academic either. It's become one of the most closely watched scientific rivalries in modern astronomy, because both groups have continued pushing their methods forward, using the James Webb Space Telescope, specifically, to try to nail down which measurement, if either, has a hidden flaw in it. Rees and the SH0ES team were awarded dedicated JWST observing time to remeasure their Cepheid targets with less crowding and interference from neighboring stars, a known challenge for ground-based and even Hubble Space Telescope observations of Cepheids sitting in busy, crowded galaxy fields. Friedman and her collaborator Barry Mador were separately awarded their own JWST time, with a proposal whose stated goal was, in its own title, answering the most important problem in cosmology today: is the tension in the Hubble constant real? As of the most recent published status reports from the Chicago Carnegie Hubble program, using both Hubble and Webb data together, the team has expanded its approach even further, now cross-calibrating three separate, independent stellar distance methods at once: the tip of the red giant branch, Cepheids, and a third, newer technique called JAB, short for J-region asymptotic giant branch stars, another category of star with a predictable brightness that can serve as yet another independent check. The fact that three of the best-funded, most careful research groups in cosmology are now pointing some of the most expensive scientific instruments ever built directly at this one specific disagreement tells you how seriously the field is taking it. Stellar standard candles aren't the only way to attack this problem, though, and some of the most compelling independent measurements come from completely different corners of physics entirely, corners that don't rely on stars or supernovae at all. One of those approaches uses something called a megamaser, an astronomical version of a laser, but built from microwave radiation instead of visible light, produced naturally by water molecules in gas clouds swirling around the accretion disks of certain supermassive black holes. By precisely tracking the geometry and motion of these maser-emitting gas clouds using radio telescopes, astronomers can calculate a direct, geometric distance to the host galaxy without needing Cepheids, red giants, or supernovae anywhere in the calculation chain. The Megamaser Cosmology project, publishing its results in 2020, measured a Hubble constant of 73.9 kilometers per second per megaparsec, with a margin of error of about 3 kilometers per second per megaparsec, landing squarely on the high side of the tension, right alongside the SH0ES result, and independently reinforcing it using a method that shares essentially no measurement machinery with the distance ladder approach at all. A separate and genuinely fascinating approach uses something called time delay cosmography, based on an idea first proposed by the astronomer Sjur Refsdal all the way back in 1964, decades before the technology existed to actually carry it out. The concept relies on strong gravitational lensing, the bending of light around a massive foreground galaxy that happens to sit directly between Earth and a much more distant, brighter object, typically a quasar, a supermassive black hole actively feeding on infalling gas. When the alignment is close enough, the foreground galaxy's gravity splits the quasar's light into multiple separate images, arriving at Earth along slightly different bent paths. Because those different light paths are physically different lengths, the multiple images of the same quasar don't just appear in different places in the sky, they also flicker and vary in brightness at slightly different times, with a measurable delay between them. That time delay, combined with a careful model of the foreground galaxy's mass distribution, translates directly into a cosmological distance measurement, and from there, into an independent value for the Hubble constant. A research collaboration called H0LICW, an acronym for H0 lenses in Cosmogreil's wellspring, spent years building up a sample of these lensed quasar systems, combining over a decade of monitoring data from ground-based telescopes with detailed Hubble Space Telescope imaging and spectroscopy to pin down the mass models of the foreground lensing galaxies as precisely as possible. Their headline result, combining 6 lensed quasar systems, came out to 73.3 kilometers per second per megaparsec, once again landing on the high side of the tension, essentially matching both SH0ES and the megamaser result. A successor collaboration called TD Cosmo, bringing together H0LICW along with several related lensing survey teams, pushed the analysis further and found something that turned out to matter enormously for how seriously scientists should take any single result in this field. When the team expanded their sample by adding 33 additional lensing systems from a separate survey called SLACS, and allowed for more flexibility in how they modeled the mass distribution of the foreground lensing galaxies, their central value for the Hubble constant dropped substantially, down to around 67.4 kilometers per second per megaparsec, matching the Planck CMB result almost exactly, with a much larger margin of error than the original H0LICW analysis had reported. That's an enormous shift, from firmly agreeing with the high-side measurements to essentially agreeing with the low-side ones, driven entirely by a change in the assumptions used to model exactly how mass is distributed inside the foreground lensing galaxies. It's a genuinely important cautionary lesson buried inside this whole story. Measuring the Hubble constant through gravitational lensing time delays isn't just a matter of collecting more light, it's deeply entangled with separate, difficult assumptions about galaxy structure, and small changes in those assumptions can swing the final answer across the entire width of the tension, from one side to the other, without any new observational data being added at all. A fourth, still emerging method uses gravitational waves, ripples in spacetime itself, produced by cataclysmic events like colliding black holes or neutron stars, first directly detected by the LIGO Observatory in 2015. When 2 neutron stars collide, and the resulting gravitational wave signal is paired with an electromagnetic counterpart, meaning astronomers can also see the event with ordinary telescopes, the gravitational wave signal itself directly encodes the distance to the source, without relying on any traditional standard candle at all. Physicists have started calling these events standard sirens, a direct nod to the older term standard candles. Following the landmark 2017 detection of a neutron star merger, observed in gravitational waves by the LIGO and Virgo collaborations, researchers used the event to derive an independent Hubble constant estimate, though with a margin of error still far too wide, at that point, to meaningfully favor one side of the tension over the other. As more standard siren events get detected in the years ahead, this method is widely expected to eventually become precise enough to serve as a genuinely independent fifth referee in the argument, one built from an entirely different branch of physics than anything else on this list. So, tallying it all up, the cosmic microwave background says 67.4. The Cepheid supernova distance ladder from SH0ES says 73 to 74. The tip of the red giant branch method sits in between, around 69.6 to 69.8, agreeing more with the low side, but not cleanly. Megamasers say 73.9, agreeing with the high side. gravitational lensing time delays, say either 73.3 or 67.4, depending heavily on which set of modeling assumptions you use for the lensing galaxies. And gravitational wave standard sirens are still too imprecise to vote either way, for now. If this all sounds less like a single, clean, two-sided argument, and more like a genuinely messy, unresolved cluster of results pointing in several different directions, depending on exactly how you measure things, that's because it is. And that messiness is itself one of the most important things to understand about the current state of the Hubble tension. It isn't simply early universe versus late universe, the way it's sometimes summarized in headlines. It's early universe against a majority, but not the entirety, of late universe methods, with at least one late universe method, the chi-RGB approach, sitting awkwardly in between, and another, gravitational lensing, capable of landing on either side, depending on modeling choices that have nothing to do with new data at all. None of this messiness has stopped physicists from trying seriously to explain what's going on, and the proposed explanations generally fall into two broad categories. Either there's a hidden, systematic measurement error sitting somewhere in one or more of these techniques, or there's genuinely new physics missing from the standard cosmological model that none of these methods were built to account for. On the systematic error side, researchers have spent enormous effort searching for anything that might specifically be biasing the Cepheid-based distance ladder high, since that's the method producing the most persistent tension against the CMB result. Possible culprits that have been investigated include crowding effects, where a Cepheid's measured brightness gets subtly contaminated by the light of unrelated, overlapping stars in a busy galaxy field, and uncertainties in exactly how much interstellar dust dims a given Cepheid's light before it reaches our telescopes. The push to observe with JWST specifically targets the crowding problem, since Webb's sharper resolution should, in principle, separate individual Cepheids from their crowded neighbors far more cleanly than earlier instruments could. So far, the JWST-era results haven't resolved the disagreement, and if anything, the improved data has tended to reinforce rather than undermine the original SH0ES measurements, which has pushed more of the field toward taking the new physics explanation seriously. On the new physics side, the most actively studied proposal is early dark energy, a theoretical addition to the standard cosmological model distinct from the dark energy that Perlmutter, Schmidt, and Rees discovered accelerating the universe back in 1998. That original dark energy is a steady, constant force still acting today. Early dark energy, by contrast, is proposed to have existed only briefly, in the earliest sliver of cosmic history, contributing an extra push to cosmic expansion for a short window, before rapidly diluting away almost to nothing. Physicists first proposed in papers published around 2018 that this kind of brief, early anti-gravitational nudge could reduce what's called the sound horizon, a specific length scale imprinted in the cosmic microwave background related to baryon acoustic oscillations, and that reducing the sound horizon in exactly the right way would raise the Hubble constant inferred from CMB data just enough to close the gap with the locally measured distance ladder value. It's an elegant idea specifically because it targets the actual physical mechanism connecting the CMB measurement to the final number, rather than just adjusting a knob to make two numbers match by fiat. It comes with real costs, though. Multiple follow-up studies have found that adding early dark energy to the standard model creates new tension of its own, with independent measurements of how galaxies are clustered across large scales, meaning the fix for one problem tends to strain a different, previously well-behaved part of the model. As of the most recent research available, no version of early dark energy has been confirmed, and the field remains genuinely split on whether it's the right direction to be looking in at all. There are other proposed explanations circulating in the research literature too, including modifications to how neutrinos, the extremely light, weakly interacting particles produced in enormous numbers by the Big Bang, behave in the early universe, and various forms of interacting dark energy, where dark energy and dark matter are proposed to exchange energy with each other over cosmic time in ways the simplest standard model doesn't currently include. None of these alternatives have gathered anywhere near the level of research attention or observational testing that early dark energy has, and none of them have resolved the tension either. So where does all of this leave the field right now? Firmly split, and increasingly comfortable saying so publicly, which is itself a notable shift from a decade ago, when many cosmologists still expected the disagreement to quietly resolve itself as measurements improved. Tommaso Troy, a physics professor at UCLA who worked on a 2025 study using yet another independent lensing technique through the Keck Observatory, described the situation by saying, "What many scientists are hoping is that this may be the beginning of a new cosmological model," a striking thing to hear a mainstream senior cosmologist say openly about the field's own foundational framework. A separate 2025 analysis from the NOR Lab Research Consortium concluded that their improved local measurements effectively rules out explanations of the Hubble tension that rely on a single overlooked error in local distance measurements, directly pushing back against the idea that this is simply a matter of finding one hidden mistake somewhere in the Cepheid data. Not every recent study agrees the crisis is deepening, though. A mid-2025 analysis reported in Astronomy Now found local and CMB-based measurements whose margins of error now technically overlap, roughly 70.4 kilometers per second per megaparsec locally against Planck's 67.4, which some researchers have read as tentative evidence the tension might be easing rather than worsening. That reading remains a minority position within the field as of the most recent research available, and most published work from 2025 and 2026 still treats the Hubble tension as a live, unresolved, and quite possibly deepening problem. What makes the Hubble tension worth understanding, beyond just the raw disagreement in the numbers, is what it represents structurally. This isn't a single measurement that might simply be wrong. It's now at least 4 or 5 genuinely independent lines of evidence, built from entirely different physics, from stars to black holes to gravitational waves to bent starlight, converging into a real, statistically significant, and so far unexplained split. Every year, the individual measurements get more precise, the error bars get smaller, and the disagreement, rather than shrinking as you'd expect from random noise averaging itself out, has largely held steady, or, according to some analyses, even grown slightly more severe. And the expansion rate isn't the only place where the universe seems to be arguing with itself. Zoom out from the Hubble constant to the galaxies scattered across the sky, and a second, stranger problem shows up, one that has nothing to do with how fast the universe is expanding, and everything to do with how quickly it managed to build anything at all. Here's the basic setup for that second problem, because it explains why it exists in the first place. When you look at a distant object in space, you aren't seeing it as it is right now. You're seeing the light it emitted a very long time ago, light that has been traveling toward Earth ever since, which means looking far enough away is functionally the same thing as looking back in time. The James Webb Space Telescope was built specifically to push that ability to its limit, using infrared detectors sensitive enough to pick up light from galaxies so distant and so ancient that their light has been stretched, redshifted, by the expansion of space itself on its way to us. Astronomers measure that stretching using a number called redshift, usually written as Z, and the higher the redshift, the further back in cosmic history you're looking. Almost immediately after JWST became fully operational, astronomers pointed it at some of the deepest patches of sky ever imaged and started finding galaxies from a period called cosmic dawn, generally defined as somewhere between roughly 500 and 800 million years after the Big Bang, with the very earliest confirmed examples pushing back even further to less than 300 million years after the beginning. And a striking number of these galaxies looked wrong, in specific, measurable, repeatable ways. Some of them showed disk and bulge structures, the kind of organized, settled shape you'd expect from a galaxy that has had many billions of years to gravitationally relax into a stable configuration, not one that formed within the universe's first few 100 million years. Others showed a pattern running backward from what standard galaxy formation theory predicts, with smaller galaxies appearing more massive than larger ones, when mass is supposed to build up gradually and predictably in bigger systems over long stretches of cosmic time. Multiple surveys found chemical signatures inside early galaxies, implying active star formation had already been underway for at least 100 million years by the time the galaxies were being observed. meaning the actual first stars in those systems would have had to ignite even earlier still. And the angular sizes of many of these early galaxies, how large they physically appear once you account for their known distance, came out roughly 10 times smaller than the standard cosmological model predicts, meaning they're unexpectedly compact for how much light and mass they seem to contain. One especially influential early paper, published by astrophysicist Andrea Ferrara and collaborators, was blunt enough to put the core problem right in its title, on the stunning abundance of super-early luminous galaxies revealed by JWST. That's the crux of it. It isn't just that a handful of individual oddball galaxies turned up. It's that JWST kept finding far more bright, massive-looking galaxies at these extreme distances than existing models predicted should exist at all. A systematic excess, rather than a scattering of one-off anomalies. A few individual galaxies became genuinely famous within the field for just how extreme their properties turned out to be. GNZ11, identified using both Hubble and JWST data, showed unusually mature, extreme properties at a redshift corresponding to roughly 430 million years after the Big Bang, remarkably bright and chemically evolved for an object supposedly that young. Researchers also identified what's called a quiescent galaxy, meaning one that had already stopped forming new stars entirely, at around 700 million years after the Big Bang, which raises an uncomfortable question on its own. How does a galaxy burn through its entire star-forming fuel supply and shut down completely that quickly, when the universe itself was barely a toddler by cosmic standards? Then, in 2024, JWST broke its own distance record in dramatic fashion. Using Webb's near-infrared spectrograph across observations in October of 2023 and January of 2024, and after nearly 10 hours of dedicated spectroscopic observation, an international team working on the JWST Advanced Deep Extragalactic Survey, known as JADES, confirmed a galaxy called JADES Z140, sitting at a redshift of 14.32, corresponding to less than 300 million years after the Big Bang, roughly 2% of the universe's current age. Lead researchers Stefano Carniani of Scuola Normale Superiore in Italy and Kevin Heinlein of the Steward Observatory at the University of Arizona found the galaxy spanned roughly 1,600 light-years across and concluded its light had to be coming from an already substantial population of young stars, rather than from a quasar, because the light was simply too extended to be explained by gas falling into a single supermassive black hole. That made it, at the time, the most distant, and therefore the youngest, confirmed galaxy ever observed, and the second most luminous galaxy ever confirmed at such an extreme distance, trailing only GNZ11. Much of this early wave of discovery came out of a specific JWST program called CEERS, the Cosmic Evolution Early Release Science Survey, led by Stephen Finkelstein at the University of Texas at Austin. CEERS was one of the first large observing programs to turn Webb's cameras loose on a wide patch of deep sky, specifically hunting for galaxies from the first 500 million years of cosmic history, and its early results, published under titles like An Early Look into the First 500 Years of Galaxy Formation with JWST, were among the papers that first put the impossible early galaxy problem on the map for the broader scientific community, not just specialists. But the single strangest discovery to come out of this entire wave of research didn't turn out to be an unusually mature ordinary galaxy at all. It turned out to be something nobody had a name for yet, something astronomers eventually started calling little red dots. Little red dots are exactly what they sound like in Webb's images: small, compact, unusually red objects, showing up in large numbers at redshifts greater than 4, meaning within roughly the first 1.5 billion years of cosmic history. When astronomers started taking detailed spectra of these objects rather than just images, they found something odd. Many of them showed broad emission lines in their spectra, spectral features characteristically produced by gas swirling at extremely high speeds, the classic signature of material orbiting close to a supermassive black hole. In 2024, a team led by Dale Kochevsky compiled the largest sample of these objects to date, 340 little red dots pulled from multiple JWST surveys, including CEERS, JADES, and the Next Generation Deep Extragalactic Exploratory Public Survey. The team found that 70 to 80% of their targets showed evidence of gas orbiting at roughly 1,000 kilometers per second, about 2 million miles per hour. Strong evidence for an accretion disk feeding a black hole at the center of each object. Kochevsky's team also mapped out when these objects existed across cosmic history, finding they emerged in large numbers around 600 million years after the Big Bang, and then underwent a rapid decline in numbers by around 1.5 billion years after the Big Bang, essentially appearing suddenly, thriving briefly, and then largely vanishing as a distinct population. What makes little red dots such a direct extension of the broader impossible early galaxy problem is the specific nature of the anomaly they present. Multiple research teams studying these objects have found that the black holes sitting at their centers appear overmassive, meaning far too large relative to the total mass of their surrounding host galaxy compared to the ratio seen in galaxies today, including our own Milky Way. In an ordinary, present-day galaxy, a central supermassive black hole typically makes up a tiny, predictable fraction of the galaxy's total stellar mass, a relationship built up gradually over billions of years of coevolution between a galaxy and its central black hole. In little red dots, that ratio appears badly out of balance, with black holes that seem to have grown enormously fast relative to the stars around them, in a fraction of the time that ratio is supposed to take to establish. One striking example, catalogued through the Uncover survey as one of the most distant little red dots known at a redshift of 8.5, was confirmed through detailed spectroscopy to contain what researchers explicitly described as an overmassive black hole. The explanation for how this happened remains genuinely unsettled, and multiple competing models are actively being tested against the data. Some researchers have proposed these black holes are accreting matter at extremely high, near maximum physical rates, essentially growing as fast as the laws of physics allow, fast enough to bulk up to enormous size well before their surrounding galaxy has had time to catch up. Other researchers have proposed a different mechanism entirely, that these black holes formed unusually large from the start, through the direct collapse of enormous primordial gas clouds early in cosmic history, skipping the slower, more gradual formation pathway that produces black holes in the modern universe, essentially being born massive rather than growing massive. Some recent detailed spectroscopic studies have found that at least some little red dots show electron scattering effects in their light that were previously mistaken for extremely high black hole masses, suggesting the true masses of at least some of these objects may be smaller than first estimated, though still frequently sitting at masses that remain difficult to explain given how little time these systems had to form. Not every research team has concluded that little red dots, or the broader impossible early galaxy pattern, necessarily represent a crisis for the standard cosmological model itself. This is where a genuinely important counterchapter to the whole story comes in. In 2024, a research team at St. Mary's University in Canada, led by Dr. Guillaume Desprez and including co-author Dr. Marcin Sawicki, went back and took a second, far more careful look at some of the original claims that had generated the most attention. Desprez explained the motivation for the re-examination directly. The early results from JWST were a shock. Some astronomers suggested that textbooks would have to be rewritten, so we decided to take a closer look. Using detailed data from the Canadian NIRISS Unbiased Cluster Survey, known as CNUCS, Desprez's team searched for galaxies similar to the ones featured in the earliest, most attention-grabbing claims, at a comparable distance of roughly 13 billion light-years away, corresponding to a period when the universe was only about 5% of its current age. Their sample of 20 candidate galaxies turned out to be neither as massive nor as old as the original headline-making claims had suggested. Sawicki summarized what that specific distance actually represents. Light from those galaxies took 13 billion years to reach us, offering a glimpse when the universe was just 5% of its current age. Their conclusion pushed back directly against the idea that the standard cosmological timeline urgently needs to be rewritten based on the earliest wave of JWST results. It's also worth remembering that a version of this anomaly predates JWST entirely. A researcher named Fulvio Melia had already identified an impossible early galaxy problem using older Hubble Space Telescope data at high redshift, in papers published in 2014, 2020, and 2023, before Webb had even launched. US didn't invent this problem out of nowhere. It made an existing, smaller anomaly dramatically harder to ignore by finding dozens of new examples at greater distances, with far better data, essentially every year since it began operating. So how has the mainstream of astrophysics actually responded to this entire body of evidence, from mature-looking early galaxies to overmassive little red dot black holes? Overwhelmingly, the response has been to revise the models of galaxy and black hole formation rather than to question the age of the universe itself. Under this view, which remains the dominant position in the field as of the most recent research available, star formation and black hole growth in the early universe must have proceeded faster and more efficiently than anyone had previously modeled, whether through reduced dust obscuration letting more starlight escape and reach our telescopes, through weaker feedback effects failing to suppress runaway star formation the way models had assumed, through direct collapse formation pathways for early black holes, or through some combination of all of the above. Under this view, the universe is still roughly 13.8 billion years old, and what JWST has actually discovered isn't a crack in cosmic age, but a set of serious, previously invisible gaps in how galaxies and their central black holes actually assemble themselves in the first billion years of cosmic history. There's also a smaller but active line of research proposing that early dark energy, the same brief, temporary burst of anti-gravitational push theorized to help explain the Hubble tension, could account for this galaxy formation puzzle at the same time, by giving the early universe a head start on structure formation without changing the overall 13.8 billion year age at all. That research remains actively contested and unconfirmed, one of several serious ideas competing to explain the same body of anomalous data without resorting to a fundamentally different cosmic timeline. And then there's the minority position that does go after the timeline directly, most prominently represented by University of Ottawa physicist Rajendra Gupta, who has argued in peer-reviewed, published research that the entire body of impossible early galaxy evidence, along with the separate Hubble tension problem, makes far more sense if the universe is actually 26.7 billion years old, roughly double the standard estimate, giving early galaxies, and by extension early black holes, dramatically more time to reach the maturity JWST keeps finding. Most cosmologists treat the Hubble tension and the impossible early galaxy problem as two separate puzzles, each needing its own separate fix. Gupta doesn't. He thinks they're the same problem wearing two different masks, and he's built an entire framework specifically designed to explain both of them at once. It's worth going deeper into exactly what that framework is, and exactly how it's held up under scrutiny, because it turns out to be one of the more rigorously tested challenges cosmology has faced in decades. Let's start with the claim itself, because it's worth restating clearly before digging into the argument around it. Gupta has published a series of peer-reviewed papers, starting in September of 2023, in the monthly notices of the Royal Astronomical Society, arguing that the universe isn't 13.8 billion years old. According to his model, it's 26.7 billion years old, and additionally, according to his later work, it doesn't need dark matter to explain how galaxies and galaxy clusters behave. Gupta's model is called CCC plus TL, and it's built from two separate physical ideas stitched together. The first, covariant coupling constants, or CCC, proposes that the fundamental forces of nature aren't fixed the way physics has always assumed, and instead weaken gradually as the universe ages, over timescales far too slow to notice in any laboratory experiment on Earth. The second is an old, largely discredited idea called tired light, which proposes that light loses energy simply by traveling across enormous cosmic distances, causing it to redshift, the same signature astronomers have always interpreted as direct evidence the universe is expanding. It's worth understanding exactly why Gupta didn't just use tired light on its own, because the reasons tell you a lot about how seriously this specific model has actually been engineered. Plain tired light theories have a well-documented, decades-old track record of failing basic observational tests. They don't explain the near-perfect uniformity of the cosmic microwave background. They don't correctly predict what's called time dilation in distant supernova light curves, the way an exploding star's brightening and dimming should appear to unfold in slow motion when viewed across an expanding universe, an effect that's been directly measured and that plain tired light models get wrong. And critics have pointed out for decades that basic tired light, on its own, simply doesn't match the actual rate of redshift observed from distant galaxies. Gupta's response to these known weaknesses was to build a hybrid, keep the universe genuinely expanding, add the covarying coupling constants mechanism to help explain the accelerating expansion astronomers attribute to dark energy, and layer in only a partial tired light contribution to the redshift signal, rather than relying on tired light to explain the whole thing. It's a deliberately engineered patch job designed specifically around tired light's known failure points, not a naive revival of an old, already rejected idea. Since that first 2023 paper, Gupta has published a fairly extensive and genuinely ambitious body of follow-up research, trying to show CCC plus TL holds up against one dataset after another. In 2024, he published a paper testing the model against baryon acoustic oscillations, the frozen pattern of sound waves imprinted on the large-scale distribution of galaxies, along with the sound horizon measured in the cosmic microwave background, and reported that CCC plus TL fits about as well as the standard model does. Later in 2024, he published work specifically targeting the impossible early galaxy problem, arguing his model resolves the tension by giving those galaxies dramatically more real time to form, since the underlying cosmic clock runs differently than in the standard picture. In 2025, he extended the model further, publishing work applying CCC plus TL to galaxy rotation curves, the same kind of data Vera Rubin used in the 1970s to establish the case for dark matter in the first place, using measurements from a public database called SPARC, and reported promising results describing what he calls alpha matter and alpha energy, his models substitute explanations for the effects normally attributed to dark matter and dark energy. Interestingly, in that same rotation curve paper, Gupta noted that the acceleration scale, where his model's effects kick in, sits remarkably close to the acceleration scale used in MOND, the modified gravity theory proposed back in 1983, as an alternative explanation for the same rotation curve data, even though Gupta describes the two models as addressing the problem through unrelated underlying physics. It's a striking coincidence either way, two separate attempts to remove dark matter from cosmology, built on entirely different mechanisms, both converging on roughly the same critical acceleration threshold. Gupta hasn't been shy about the scale of what he's claiming either. In comments accompanying his research, he's described the implications directly. Sometimes the best response is the simplest response. Perhaps the universe's biggest secrets are nothing more than illusions played on us by the evolving constants of nature. It's a genuinely bold claim that both dark matter and dark energy, two of the three pillars holding up the standard model of cosmology, might simply be measurement artifacts produced by forces of nature quietly weakening over billions of years, rather than real, physical substances filling the universe. So has the model held up under scrutiny from other physicists? This is where the story gets into real, documented scientific pushback, not just general skepticism. In 2025, a research team led by Lay and collaborators published a direct test of CCC plus TL using what are called cosmic chronometers, a method that measures the age of the universe at different points in history by studying the ages of old, quiescent galaxies that have stopped forming new stars, essentially using galaxies themselves as clocks. According to that analysis, when the CCC plus TL model was fit to this cosmic chronometer data, the resulting value for the model's key parameter, called alpha, which controls how strongly the coupling constants vary, disagreed with the value derived from Type 1a supernova data by roughly 6 standard deviations, an extremely large, essentially decisive level of internal inconsistency within the model itself. The Lay team's paper describes this result in blunt terms. It falsified the version of the model tested. Gupta responded directly, publishing his own paper re-examining the assumptions behind that specific test, arguing that a fully self-consistent comparison would require recalculating certain stellar evolution and stellar population synthesis assumptions, specifically within the CCC plus TL framework, rather than importing assumptions built for the standard model wholesale. As of the most recent research available, that specific disagreement between the Lay team's falsification claim and Gupta's rebuttal remains an open, actively contested technical dispute, exactly the kind of back and forth that's supposed to happen in functioning peer-reviewed science, and exactly the kind of dispute that hasn't yet been resolved in either direction. There are other open weaknesses in the model that even sympathetic science coverage has been upfront about. Gupta's model has, as of the most recent published research, not yet been tested against gravitational lensing, the bending of light around massive objects, an area where the standard dark matter model already does an extremely good job explaining what astronomers observe. Since lensing is one of the more direct, geometrically clean tests available in cosmology, that's considered a significant gap, and one Gupta himself has acknowledged, going as far as proposing that gravitationally lensed images of the same distant object, arriving via different bent light paths of different lengths, might eventually offer a way to separate out how much of an object's redshift comes from cosmic expansion versus how much comes from the tired light component of his model. There's also a more fundamental issue sitting underneath the entire framework. Nobody has ever directly detected the coupling constants of nature actually varying, in any laboratory experiment, in any astrophysical observation, in any context outside of Gupta's own cosmological model fits. The variation is inferred entirely from how well it makes the model match observational data, not measured independently through any other means. That doesn't make the idea wrong, but it does mean the entire CCC mechanism currently rests on a physical effect that has never been directly observed to actually occur. It's worth putting all of this in a wider historical context, because Gupta's challenge to the standard model isn't the first serious, mathematically worked-out attempt to unseat Big Bang cosmology. And looking at how the earlier attempts actually played out tells you something useful about how these disputes tend to get resolved. Back in 1993, Fred Hoyle, the same astrophysicist who coined the term Big Bang mockingly back in the 1950s, teamed up with astronomers Geoffrey Burbidge and Jayant Narlikar to publish a revised version of Hoyle's original steady-state theory, called Quasi-Steady-State Cosmology, or QSSE. The original steady-state model had been effectively killed off by the 1965 discovery of the cosmic microwave background, since steady-state cosmology, in its simplest form, had no mechanism to produce that kind of leftover radiation at all. QSSE was a deliberate attempt to fix that specific hole, proposing that the universe goes through long cycles of expansion and contraction, punctuated by localized bursts of matter creation the authors called little Big Bangs, occurring around extremely massive objects, with the whole system oscillating over a period of roughly 40 billion years, while still avoiding a single, universal origin point. Hoyle, Burbidge, and Narlikar published a genuinely substantial body of work defending and refining the model through the 1990s and into the 2000s, arguing it could explain everything from the abundance of light elements to the structure of the cosmic microwave background itself. It didn't hold up. Physicist Edward Wright at UCLA published a direct rebuttal showing that QSSE's own equations predicted a specific, testable consequence. A large fraction, somewhere between 75 and 90% of radio sources in certain bright samples of the sky should appear blue-shifted rather than red-shifted, based on how the model's oscillating expansion was supposed to work. That prediction simply isn't what astronomers observe. Separately, when Narlikar, Burbidge, and a collaborator later claimed the model could fit the detailed anisotropy data from the WMAP satellite's map of the cosmic microwave background, other researchers found the fit depended on adjustments to the model made specifically, after the fact, to accommodate that data, changes described by critics as poorly justified given how loosely motivated the underlying model already was. QSSE never gained meaningful traction beyond its 3 original proponents and a small number of collaborators, and today it's treated in the field as a serious, well-worked-out historical attempt at an alternative cosmology that ultimately failed its observational tests, not as a live competitor to the standard model. That history matters here for a specific reason. It shows what actually happens to alternative cosmological models over time in this field. They get published. They get taken seriously enough to generate real, substantive rebuttals from other physicists. They make specific, checkable predictions. And then those predictions either hold up against new data or they don't, and the field moves on accordingly, often after years or even decades of genuine, good faith back and forth. Gupta's CCC plus TL model is currently somewhere in the middle of that exact same process, a peer-reviewed, actively defended, and actively challenged alternative, generating real technical disputes like the one with the Ley team over cosmic chronometer data, rather than having already been dismissed outright or having already won over the field. So where does that leave things right now? For anyone trying to figure out how seriously to take the claim that the universe might be twice as old as we think, the honest answer is that it's a genuinely open, actively contested piece of research, not a settled crank theory, and not an emerging consensus either. Gupta's model has cleared a real bar that most alternative cosmological proposals never reach: publication in respected, mainstream peer-reviewed journals, a growing and genuinely wide-ranging body of supporting papers addressing multiple independent datasets, and now, direct, technical, published disagreement from other researchers testing it against data Gupta himself didn't originally use. That combination, serious enough to generate real scientific opposition, is actually a meaningful marker of a theory being taken seriously within the field, even by the people arguing it's wrong. What it hasn't done is convince the overwhelming majority of working cosmologists, hasn't been tested against gravitational lensing, and rests on a mechanism, varying coupling constants, that's never been independently detected outside of the model's own data fits. The universe's age remains, officially, and for the vast majority of the field, 13.8 billion years. But for the first time in decades, there's a peer-reviewed, mathematically detailed, actively defended, and actively contested alternative sitting on the record, arguing for 26.7 billion years instead, going through exactly the kind of rigorous, adversarial testing that over the past century has determined which challenges to the standard picture of the cosmos survive and which ones don't. Whether CCC plus TL ends up remembered the way quasi-steady-state cosmology is remembered now, a serious, well-fought attempt that ultimately fell to the data, or whether it ends up being the thing that finally cracks open the number everyone assumed was settled, is still, as of right now, a genuinely open question. And that, more than any single number, is the real story here. The age of the universe isn't a fact sitting quietly in a textbook. It's an active, ongoing argument, being fought out in peer-reviewed journals right now, by people who take the possibility that they're wrong seriously enough to keep testing it.